Okay, what I have here is I've got a Carnot cycle, okay, air in a piston cylinder assembly. So remember, a Carnot cycle is a reversible cycle that goes between um, isothermal processes, that'd be 1 to 2 and 3 to 4, and then isothermal processes, I'm not, excuse me, adiabatic process 2 to 3 and 4 to 1. Okay, this is a heat pump that I've got here, not a power cycle. Okay, so the hot and cold temperatures are 600 and 300. I know that hot heat transfer, that would actually be Q out for a heat pump. Okay, um, is 250 kilojoules per kilogram. Okay, I know the pressure at the start of at the thermal expansion. This is P1 equals 325 kilopascals. That's where my isothermal expansion starts, right? This is a constant temperature line here. Okay, so it wants me to find the work of the cycle. Okay, so what I recognize here is it's a Carnot cycle. It's a reversible cycle. Okay, so if I want to find the work of the cycle, okay, I have Q out or Q hot. I just need to find Q cold, and then I can subtract those two things to get the work of the cycle, right? Because Q in minus Q out gives me the work. Okay. Now, because it's a reversible cycle, I can find that would be Q cold just from this ratio like this. And again, I have this simply because it's a reversible cycle. For all reversible cycles, okay, hot reservoir is that ratio is related to Q. Therefore, QC, which is what I'm looking for, is going to be QH, which is 250 times 300 over 600 equals 125. Therefore, the work of the cycle equals Q hot minus Q cold, 250 minus 125 equals 125 kilojoules per kilogram. So that's the work of the cycle. Again, recognizing that ratio for a reversible cycle. Okay. The next thing I have is I want to find the pressure at the end of the isothermal expansion. This is essentially P2. Okay. Again, I know P1. I'm looking for P2. I know the temperature going on here. I know this is isothermal expansion. So isothermal means, again, T1 equals T2. For air, it's an ideal gas. If I look up my U values, they only depend on T. Therefore, U1 equals U2. Now, from the first law, if delta U is 0, then Q1 to 2 equals the work 1 to 2. Okay, which equals, that is Q cold, which I just found. Well, not there, right there, right? Equals 125. So again, because it's constant temperature, it's constant energy. Because it's constant energy, then heat equals work, which equals what I already calculated to be, which is 125 kilojoules per kilogram. Okay. Now, knowing that it's air at isothermal, okay, I can find the work, which is equal to the heat, using this equation right here. Okay, so the work, or Q 1 to 2 equals work 1 to 2 equals, again, that would be RT times the natural log of V2 over V1. Now, the thing is I want to find my pressures. Again, going back to the fact that this is a polytropic process, isothermal process where N equals 1, just like I used this equation, now I can come in here and relate pressures with volume. So I plug in N equals 1, and it basically, the pressure ratio is the reciprocal of the volume ratio for constant temperature, when N equals 1, isothermal. So instead of that, I can use RT times the natural log of P1 over P2. And there you have it. Now I know everything here. I can say, okay, 125 kilojoules. RT, that's going to be 8.314 over 28.97. Again, because it's air, this is the R bar value. That's molecular weight of air times the temperature. The temperature at this point, again, is the cold one, so it's 300. Times the natural log of the pressure ratio. And again, pressure 1 is 325 all over pressure 2. Through the magic of algebra, we can then find that the pressure at state 2 is 76.1 kilopascals. Again, all we do on this one is recognize temperature is constant, so energy is constant, so heat equals work. Then I know that because it's isothermal, my work is this, and my volume ratio is the reciprocal of the pressure ratio because it's isothermal. And then from that, the only thing I don't know is pressure 2, which is what I'm looking for.